All right, folks, let's go ahead and get started. My name is Sharon White. I'm the marketing manager for BLT. So welcome to today's webinar, Optimizing FPGA Designs with Vivado Reports and Design Rule Checks. If you have questions, please put them in the chat panel. We will get to them at the end during the Q&A. We'll do our best to answer all of your questions, but do please keep them on topic. And if we don't get to your question, you can always email us with other questions. Today's webinar is being recorded. We will send that recording out once it's ready. It does take a few days, so look for it at the beginning of next week. There are no books or slides provided with today's talk. So now let me introduce to you BLT. BLT provides electronic solutions and engineering design services. Our headquarters are in Maryland, and we have a design office in Melbourne, Florida as well. We design chips, boards, software, and complete systems for commercial, aerospace and defense, and intelligence clients. Our expert engineers are known for providing robust solutions on time, every time since 1989. And some of our most notable designs include the prototypes for HDTV and satellite radio and our work on the Mars rover. Our designs are literally in space, undersea, and everywhere in between. And we've been teaching AMD Xilinx training for over 25 years. We're an AMD Premier Partner and Authorized training provider. Our training is by engineers and for engineers. All of our instructors are either engineers currently engaged on projects like Tom, or engineering managers currently managing projects. We bring our decades of real-world design experience to the classroom for you. And if you're interested in other training from BLT, be sure to follow us on LinkedIn, Facebook, Instagram, and X. I've put all of those handles into the chat panel for you. I post all the latest updates on our social pages, so if you want to be the first to know, please follow us on social. So today's webinar is being led by Tom Johnson. Tom is a project engineer at BLT, primarily focusing on adaptive SoC, RF SoC, and MP SoC designs for both commercial and defense applications. Tom was recently a team lead on a sophisticated radar design using an RF SoC, and Tom is currently working on another satellite radar design for a major defense contractor. He's a long history of producing digital hardware containing FPGAs for mission critical, industrial, and communication applications. So welcome, Tom. And before we get started, I just wanted to touch briefly on BLT's capabilities. You know us for our training, but most of the work we do is our design services. And here's a short list of our capabilities. I promise I won't read it to you. Sorry, Tom. And if today's webinar doesn't provide you with the help that you're looking for, we do have other options. So for instance, Tom, if you go to the next slide, we have our experts exchange. One of our expert engineers will come to you in person for a 4-hour customized seminar for your team with an additional 4 hours of consultation time. It's a great way to get the customized help you need for your team to move your project forward. And do note it's only available within the continental US. So I will drop the link into the chat panel for you for that. And I've also put the contact information and how to check out our courses into the chat panel. So everything's there for you. If you have any questions, you can always message me during the webinar. And otherwise, Tom, I'm going to pass it over to you.
Good afternoon. As Sharon said, my name is Tom Johnson. I'll be leading today's webinar on optimizing FPGA designs with Vivado Reports and Design Rule Checks. So let's get started. So today we'll be basically going through a presentation to introduce the many Vivado reports that are available to help you optimize your designs. We'll also focus on design rule checks types of reports and including the methodology reports. We'll then follow up with a live demo where I'll open up Vivado and go through and generate some reports and talk about the highlights of the reports, and then we'll wrap up at the end with Q&A. As Sharon said, please feel free to drop questions in the chat window. If it's appropriate with what I'm talking about, I may have a chance to answer it then in real time. If not, we'll get around to them at the end. So the Vivado Designs Suite generates different reports at different stages, such as synthesis and or implementation. Timing reports, such as the timing report summary, check timing, clock, networks report, the clock interaction report, and the clock domain crossing report help you determine why the design fails to meet its constraints. Other reports, or actually fails to operate as intended when you put it on the board. Other reports, such as the DRC report, the design rule check report, or the methodology report, help you to determine whether the design is meeting certain rules. After implementing a design, the timing reports are generally used to determine overall design performance. The timing summary report is the main report and is created automatically by the synthesis and the implementation runs. In the synthesized design, the Vivado IDE timing engine estimates the net delays based on the connectivity of the fan-out and generates a report. In the implemented design, the net delays are based on actual routing information. The report gives very detailed information about each static timing path. The timing summary report has a filtering capability which tunes your timing analysis for what you want. It has options such as type of analysis, start, through, and endpoint selection, path selection, and it also reports unconstrained paths. Because sometimes you'll get a timing report that looks like everything passed, but then you realize that you had a bunch of paths that weren't constrained, and the timing engine is not adding any limits to them. The report can be further customized by selecting the amount of detail or the number of paths that you want to see in your report. This report checks ports, pins, and paths against the current timing constraints. So basically it identifies possible problems with the design data and timing constraints before running the report timing command. So these are all checks where, again, it would be things that you don't have properly constrained. So therefore the timing engine can't properly manage the layout when it's doing the routing. So this report runs a series of default timing checks and reports a summary of any violations found. It finds out whether there are any clocks, input or output delays, or partial input or output delays, or unconstrained endpoints present in the design. It also finds out if there are any generated clocks, loops, or multiple clocks present in your design. The clock networks report, as shown here, provides a tree view of the clock trees in the design. Now, in this case, there's only one real clock and one virtual clock. Each clock tree shows the clock network from the source to the endpoint, with the endpoint sorted by type. So as you can see here, you've got your clock pin P, which is your main 300 megahertz clock, and it knows from the constraints what the speed is. And then when you click the down arrow there, it expands all the way down to then the various cores. And it lists in here clock buffers, if they're MMCMs, things like that, all of those are in there. The utilization report gives utilization of resources such as LUTs, registers, FIFO clocking, and IO resources on the target part, given by the current synthesized or implemented design. It can be viewed as a table or as a histogram. The report is returned to the standard output file unless -file or -return string or the name arguments are specified. Report DRC. The design rule check report checks the design against a specified set of design rules and reports any errors or violations that are found. As you can see here in the report, that there are thousands of possible reports that you can checks that you can run, and depending upon what part of the design you're in, you would turn on or turn off certain ones. And it says that this runs a default set of rules as shown here when you open the window or when you run it from the tickle command. And then, of course, you can also, if you have this scripted, you can turn on and turn off certain rules checking as part using the is enabled property. But DRCs are commonly run as part of the automated synthesis and implementation steps before it actually completes a route. Okay, so here's an example of a design rule check report. And basically it's listing out for you some examples as shown here of critical warnings or warnings. So basically rule violations are categorized by severity and are color coded as follows. The advisories are provided general status, or sorry, they provide general status reports and feedback on the design that's being processed. Warnings indicate that design results might be suboptimal because constraints or specifications might not be applied as intended. Critical warnings indicate that certain user input or constraints will not be applied and do not adhere to best practices. It is highly recommended that you examine these issues and make changes. Note, critical warnings are promoted to errors during bitstream generation because they deem the tool deems that your design is not valid. And errors, of course, indicate that an issue has been found that renders the design results unusable and cannot be resolved without intervention. At that point, the design, if it's automated, if it's running a DRC report as part of the automated processing, it will halt the design flow if it hits an error DRC. Okay, report methodology. The methodology report specifically checks for compliance with methodology DRCs based on the ultra-fast design methodology as documented in User Guide 949. It checks the current design against a specified set of methodology checks and reports any errors or violations that are found. Methodology checks are a special class of design rule checks, as we talked about in the previous slides. The methodology checks are a necessary part of the design flow and should be considered mandatory after implementation and prior to generating a bitstream. And here's an example report from a methodology report. And again, they list out the various ones. Now, we're looking here at the text version of the report that you'd see if you ran it in the Tickle window. If you ran this in the Vivado window, as you'll see when we do the demo later, you get a more graphical version, and the various details are listed hierarchically, so you can roll them up or drill down for detail. But shown here, there are several different methodology reports listed. Again, it gives 3 different classifications: advisories, which provide general status and feedback; warnings, which indicate the design results might be suboptimal; and critical warnings, which indicate that certain user input or constraints will not be applied or do not adhere to best practices, and that changes need to be made. Okay, report design analysis. The design analysis report provides information on timing path characteristics, design interconnect complexity and congestion. The information can be used to make design or constraint changes that improve quality of results and possibly alleviate routing congestion. Okay, so here is one of the outputs, and this is showing the GUI version of the output. And basically, with this version of the design analysis report, it's showing the worst case setup and hold paths for based on which ones have the worst slack, and for both intra and inter clock routes. And this looks like part of, and it actually is part of the report that's also in the timing summary report. Okay, report clock interaction. The clock interaction report analyzes timing paths that cross from one clock domain into another or from one source to destination. It helps to identify cases in which there may be loss or metastability issues. As shown in the figure, the clock interaction report displays as a matrix of clock domains with the source clocks in the vertical axis and the destination clocks in the horizontal axis. And then it's color coded as shown here, and they give you at the bottom, they do show the legend here, but it's color coded. So black squares indicate that there are no paths between the 2 clocks, i.e. there are no paths from a flip-flop on the source clock to a flip-flop on the destination clock. So that's there's no CDC issue there. Green squares confirm that the paths between the 2 clock domains are properly constrained and there's proper circuitry in place. Dark blue squares indicate user ignored paths that have set false path assigned to all paths between these clock domains. And quite often you'll have set false path, or you're dealing with like a JTAG control, things like that. Things that you don't care about timing because they're never used at the same time. Red squares indicate unsafe clock domain crossings that have no harmonic relation, as in they're asynchronous, and there are no exceptions in how they're handled. So these would be ones that or anything in red would have to be fixed before you continue. Light blue squares indicate partial false paths. Some paths have exceptions and some do not. So you should be a little concerned about the light blue ones. And then so we have gray squares, which indicate that all domain crossings only have a max delay data path exception. Again, this may or may not be an issue. A lot like the set false path, where you've already made a determination that there's, even though there are clock crossings there, they're not there's no significant issue other than you setting the max delay data path. And then orange squares are nearly as unsafe as red ones. Some paths have no exceptions, and the clocks are asynchronous. Also at the bottom here, it shows a table for the different clock domains. It's basically one row for each block in the matrix. And then you actually have the ability and you'll see this in demo, where you can right click on one of those rows and you can apply constraints right there. You got constraints and exceptions as needed if you realize that something was omitted. Okay, report CDC is the next one. The clock domain crossing, or CDC report, performs a structural analysis of the clock domain crossings in the design and gives you information to identify potentially unsafe CDCs, which could lead to metastability or data coherency issues. Again, this would be used hand in hand with the previous clock interaction report. It focuses on structures and their timing constraints, but does not provide information related to timing slack. Okay, and here's an example of the CDC report. And again, you can see that it uses the three levels of warning, of severity, of info, warning, and critical, depending upon what it sees as issues with these different clock domain crossing events. Okay, report exception. The exception report is only available through the TICL command line. Using the TICL command line report exceptions, it lists the timing exceptions which are affecting the timing analysis and highlights timing exceptions that are ignored. So if you've put them in various timing exceptions in, and you don't think you're getting the results you expect, you run this report, and it can tell you for some reason there was something wrong with the way you put in one of your get cells command or something like that. Your get ports command isn't returning the values you think it is, and therefore it's being ignored. Okay, the report Bus Skew is used to generate a Bus Skew report. The Bus Skew report includes two sections: a summary and then a Bus Skew report by constraint. And here's an example, and it's showing here. This is in the GUI version, and they're showing the summary here in the table. But then you can drill down into individual constraints and see the cells and the routes that are associated with that. Okay, reporting power. The power report runs the power estimation based on the current operating conditions and displays the report accordingly. The report configuration screen allows you to set the environmental conditions on the first tab, and that's what they actually have shown here. The power supply conditions are in the second tab, and basically it lists all of the power supplies and their nominal voltages. But knowing, obviously power is a square law function to voltage. So you have to know that when you turn up your voltage by, say, 10%, your power is going up by 21%. So the voltages for your power supplies are important to your power result. The third tab is your switching tab, and you can go in and give very detailed predictions of how often the flip-flops are switching, because most of the active power is consumed in toggling of flip-flops. The usual rule of thumb that's allowed is 12.5% or 1/8. Because based on considerable modeling by FPGA houses like Xilinx, they've come to the conclusion that that's a good general rule of thumb. So if you don't have detailed information available from a simulation or from real-time capture, you can just use the 12.5 as a general thumb. And then the fourth tab here is output, and that one allows you to tell it to write to a file or things like that. Okay, report QOR suggestions or quality of results. The QOR suggestion report is only available through the tickle command. It provides a list of recommendations to improve timing closure based on design changes or by setting additional constraints and tool options for the synthesis and implementation steps. The report must be run on a design loaded in memory after synthesis or after any implementation step. The analysis uses a combination of netlist characteristics, timing violation, and congestion information to give recommendations. Now, the report QOR can also give you a metric that how much it's recommending or it's estimating that your design will actually complete successfully. And depending upon which stage of the design, whether you're at the synthesis stage or you're at the implementation stage, it'll give you predictions of what's the probability your design will route successfully and whether it will actually run as expected. Okay, the SLAC histogram is next. Not every design will meet timing on the first try. You may have to guide the tools to a solution when timing fails. So this report that can be pulled up by doing reports, as shown here, timing, create SLAC histogram, and the past SLAC histogram is used to view the overall performance of the timing paths in the logic design. The SLAC distribution from the SLAC histogram provides a picture that helps in locating parts of the design that may have the worst timing problems. It may also be useful when you're doing things like allocating P blocks to lock down certain parts of your design. And here's an example of the output from the SLAC histogram. This histogram view consists of a bar graph along with an object table. In the bar graph, the number at the top of the tallest bin indicates the number of paths in the bin. When the histogram is generated, you can select a maximum or minimum delay, setup or hold option, and you can create this histogram using the create SLAC histogram tickle command as well. Okay, so we've gone through and we've introduced a lot of different reports that can be generated from within Vivado. And many of these or all of these can be bundled up in automatic report strategies that are built into the tool, and based on that, you would have a synthesis report strategy that you would tell it to run, and it would automatically run those reports for you when it does a synthesis. Similarly, you can have a default implementation report strategy shown here in the window. And then when you do your synthesis and your implementation, it will automatically run those reports for you. And depending upon the stage, the design complexity, user preferences, a different set of reports needs to be generated automatically. And the Vivado IDE allows the creation of new report strategies which are saved with user preferences, in addition to several predefined synthesis and implementation report strategies that are available by default. Okay, and like I said, we went through and introduced a bunch of different reports, and the ones I introduced, I believe, are the most significant. But you can see here from this list that there are many other report possibilities that are also in the Vivado tool that you can pull out as needed. Okay, so let's move to the demo. Okay, so I already have Vivado open here in our server. We'll start off by loading this recent project UART_LED. Now the project that we're loading is one that already has a successful synthesis and implementation, and you'll see that here in the project summary. We'll go through the project summary here when we start off, but then we're going to then start pulling reports at various levels, and you'll see how some of them are predictive, and some of them then report the results at the end. So as shown here in the project summary, of course, we know the project name, your LED. It gives us a location that we're using here. It's told to use an eval board, and it knows, of course, what part that is. Top module name, again, your LED. And then, talks about the board here. But you scroll down. Now it is telling us the status of the design at this time. It is complete. It did route. But like I said, we'll go back and look at some of the synthesis information here shortly. It gives us a DRC summary, and all of these things you're seeing up here were all part of that default implementation strategy I was talking about earlier. And you can see here your report strategy, Vivado implementation default reports. That was the strategy that was there. Now I saw somebody try to raise a hand, but what we can do here is put the things in the questions in the chat window. But that's the only way we can respond. Okay, so continuing, they said there were no DRC reports in this run. Timing, and we'll run a full timing summary later. But you can see here that in the implemented report, you can look at your setup timing results, your hold timing results, your pulse width results. We get down here to utilization, and again, part of it, we have the histogram here, the bar graph for post implementation. We can see it as a table, we can see it as a graph, and then over here, here's the power run, and again, we can see the summary here. We can also then look at the breakdown of where the power is being consumed, and this is all part of the standard power report. So let's go ahead and drill down a little bit. Let's go ahead and open the synthesized design here in the Flow Navigator. This is obviously a very small design. It lets us load it quickly and run reports quickly. It's not representative of a part that fill up this device. It's fairly empty at this point. Okay, so we've opened the synthesized design. This could have been done also from the Tickle console, just like I did it from the Flow Navigator in the GUI. So now that we've opened the synthesized design, you can see that there's a whole list of reports that are part of this default availability here under the network, under the synthesized design. We can pull out the timing summary we talked about. We can report clock networks. We can report clock interaction, methodology, the DRC, report utilization, report power, all of those things that we talked about earlier. Also up here under the reports drop down, we have a lot of the same reports, but then there are additional reports like here under timing. There's a bunch of additional reports there. So there are many different reports you can pull out at this stage in the design. So let's go ahead and proceed with the report timing summary, which, as we said earlier in the slides, is normally used as the final sign off of the design. Now, of course, that requires you to have proper constraints, but that it also this report actually helps you understand if you're missing constraints as well. Like it says here, this is a default setup, and it says report unconstrained paths. You can limit the number of paths. The default is 10. You can have more or less. Displays the 3 significant digits and number slack. There are a couple other things here under options. There's advanced, and you drill down into that a little further. You have timer settings for what corner, the process corner. Normally by default it does the slow and the fast, min and max, but you can specify which process corner you want it to run to. Of course, we have the question mark down here. Every one of the reports in the GUI has the ability to pull up additional information. So when you click on the question mark, it gives you more detailed information about it. Of course, you can also get this information from the user guides, and that's actually specified here at the bottom. User guide 906 gives full details, but it tells here all of the different things like I was showing you in the GUI of how to select options, path limits, path display, what's in the report, what's in the file output, other things. So that's all available in help. Of course, if you had run timing summary, actually I'll show that here in a minute. So let's go ahead and proceed with running it. So it gave us the results down here at the bottom, and defaults to the timing summary. Now this was at the synthesis state, and it's predictive. It doesn't have everything here, but you can see you have the general information for the design, when it was run, what was the tool version, things like that. It tells you what the timer settings were and like the corners and things like we just saw in the GUI. And then it gives a design timing summary. And normally you'd want everything here to be positive slack in all cases. So right now that we have positive, worst case, positive setup slack, but hold, excuse me, we have some negative slack and hold for 47 routes. And then of course pulse width was fine. So we'll drill down a little further. Now the clock summary, we only have one clock in the design. It's 125 megahertz. If there had been a methodology run, that there would be information brought up here, but it hasn't been run yet. So here's the check timing. Now that we talked about these earlier, these are a bunch of checks they could have. And basically it went through and said, well, there are no violations here. So none of these things occurred. They're all zeros, so that's a good thing. Let me skip over the one that's got the problem in it. But then, path groups, it would be listed. Ignored paths would be here. Unconstrained paths would be here. But what we are failing with the red dot here is under the intra-clock paths. Now, one way we could drill this quicker is we could just click on this button up here and say show only failed clocks, and then all of the things that are passing disappear, and the only thing that's shown then is the problem. But let's go ahead and look into that. So if we drill in, we see that the intra-clock paths are where we're seeing a problem. Again, hold slack is negative, and then it lists some 10 of each. So set up, these are all passing, so they're all good. And then we have the hold, and then this is showing us our worst 10 violations, or as it's predicted, because it isn't routed yet. This is a synthesized design, but it gives you an idea of what the tool has to deal with. And these are pretty large slack numbers. And you can then go in here. You can get the summary by just clicking on it over here in the path properties window. Similarly, you can, if you just double click on it, it'll put it up here in this window, which is much larger. And you can see details about the route. You can see what the clock delay path is. You can see the routed delay path, clock delay and the data path. And if you go up here to the slack where it's recommending or it's predicting a negative 1.7, you can click on that and it'll tell you that, oh, well, the clock path is longer. So it says the required time is 3.69 seconds, but it's arriving at 1.9. It's arriving, the data is arriving before the clock does, so you have a hold problem. And you can then drill down into here and see that that's literally what you have. Here's the required hold time down here, but here's your arrival time for the data. So it's currently, again, it's currently negative. Now you also, if you wanted to look at the route of the circuit, you could look at the, right click on this and do schematic, and it'll drop right up in here what your schematic of your issue is, and you can see that how the data and the clock get there, which routes. Now we generated this from the GUI. You could have also done this from the Tickle console, and just up arrow. And you can see already that this is all of those defaults that we had, because it copies the report. Everything that you do in the Vivado IDE is also copied into here. But let me show you again about the help available. Just like you saw that in the GUI, you can also get help information down here in Tickle. And all of this information is available. Like we saw earlier about what the arguments, what the options are, how to use them, what their outputs look like. And similarly, we could have then actually run the report, but this will be a text-based result. But here you can, okay, actually it's not, because of the one argument that was in there. So let me rerun that. And let me take out the name. Okay, see now we get it. The same information is here now in your tickle output. So basically, all of these details. It's not a nice, pretty GUI, but you can then query this if you wish. Parse it, as you need it with your design. Of course, you could also add additional arguments to pull out just the parts you wanted to see. Show that part. Okay, so let's go ahead and show a different one instead of the large report, the report time summary. Let's just look at the check timing, which was, as I said earlier in the slides, is sort of like a subset of that. So to get to that, we have to go to reports, timing, check timing. And again, it's those 12 checks that we saw in the timing summary report. And let's tell it to go ahead and do it. And now you can see that again, here are those 10 checks that we saw in the timing summary report, just brought out as just this one report by itself. Now, notably, the IDE is keeping all of this available for us. So we had these different tabs, we've been given it names. So the timing summary is still here, all that we looked at. So then the check timing output is here beside it. Okay, so let's go next to the report clock networks. And output in network 1. And like this will look a lot like we saw in the slide, except here we don't have a virtual clock defined, it's just a one clock. And you can see we have all of these different parts in series with it. We can, if we want to see what this looks like in the schematic, we can bring this up here. Let me zoom in on just that little piece at the top. Because then we have a whole lot of loads at the end. We've got, here's basically this chain that you're seeing where it comes in. It goes through a diff input for the clock pin, clock in P, clock pin P, clock pin N. Then we've got a buff control instance, iBuff control. We have a global clock with clock enable in here next. And you can see these things as you go through down this list. And then we have then a bunch of loads that are where this routes to. And you can expand this further. You can go see the same kinds of things you see up here. You can see it all in here by drilling down. If you had a design with multiple clocks, you would have multiple listings here, and you could then expand each one individually and see how the chain looked. This is useful sometimes because constraints will be applied on a clock early on, but then it's not being applied at the beginning. So you have to always make sure that your constraints are applied on the absolute source, and you can use like a get pins to say, okay, here's a clock. You could do like a get pins object, and it would return this pin name for you. So you could apply the constraint to this pin name, and then everything downstream would have that constraint attached to it. So it's very useful to get an idea of how the chain works, and make sure that you're applying the constraints to the right pin or to the right object. Let's close the schematic. All right, so we talked about the report clock networks. Now, unfortunately, this design only has one clock. I'm going to bring up the clock interaction report, but it's kind of underwhelming because we only have one clock. So we have, the source, destination, clock to clock. It is properly constrained in this project, so it shows up green. Of course, you have the legend down here of all the possibilities. And then here you have then a row for each interaction. And you can right click on this and you could do a report timing. You could set clock groups or false paths or multi-cycle or max delay. And of course, you could export all of this to a spreadsheet. But the clock interaction report is in your typical design where you have at least a half a dozen clocks. This is a fairly busy matrix, and it's important that you understand every clock domain crossing and that it's properly constrained, properly implemented. If it's not, you will have issues in your design that may not show up in simulation, but it will affect your design when you get to the hardware. Okay, clock interaction. Let's move on to the DRC report. So our time's going. So let's run report DRC. And like we saw in the presentation earlier, there are lots of different reports, opportunities here. You drill in to see what other details are down in here. You can turn on or off any one of these reports. I'm going to run it with the standard list. Now, all rules are at this version of Vivado. There are 2,483 rules, and some of them are turned off, as you can see with the black squares. And for this point in the design, with synthesized design, you don't want all of them on because it'll give you errors that aren't meaningful to you. But if you run it with the defaults, and of course this design was already run previously, so it's going to come back and say, no violations found. There weren't any issues in here. But if there were, you would see some with warnings or some with critical warnings or just some that are informational. And in general, design does not come back with no. There are almost always a cluster of info ones that are still around and maybe even some warnings, but you want to make sure that you clear all of the critical warnings and before you proceed. Similarly, we have the report methodology, which is not checking on discrete design rule checks per se. It's in this case, they are rule checks, but these are more like a methodology, more of the ultra fast design methodology recommendations that as I mentioned earlier, the user guide, I think it was 949, that Xilinx, AMD Xilinx has come up with to help you succeed and give you a predictive understanding of whether it's going to meet timing meet timing and operate as expected when you produce a design. So I'll go ahead and run that with the the defaults. And you can see here that it's actually concerned about this clock skew. And this clock skew is what caused the predictive, because we're still in the synthesized design. We're not the routed design. And it's saying, well, we have some large clock skews here, and we're concerned that may cause problems with your routing. And so they're in here, but they're just warnings. You can turn warnings off if you want to. But they're warnings that there's something that may be a concern. Now, understand the timing engine has the ability to move things around, especially when you have a fairly empty part, and it can move the LUTs around, so it can cause a longer data delay to force the hold time to be positive, hold skew to be positive. So we'll see that when we get to the routed design. Okay, so yeah, that would be the next thing. Let's go ahead and now go to the implemented design. So I'm going to close the synthesized design. Open the implemented design. And again, now we're in the implementation. You can see again, we have a lot of the same reports here. Now these aren't reporting on predictive information. They're now, since we have an implemented design, they're reporting on the actual routes, the actual placement of LUTs and wires and such like that. And similarly, we have this list here. We also have, up here under reports, reports. Again, there's a large list here. A lot of them are the same, but again, they're dealing with actual routing as opposed to predictive. And as you see, automatically it brought up the timing summary report. And you can see here when it did route, it did move things around. If you highlight the display, if you look, there's nothing failing, so this is not lit up, so I can't do it. And of course you see here you have negative slack. There are no negative slack; they're all positive. If we go down here and look for the intra-clock timing, remember we had those errors earlier. We had hold errors. Well, now here's the worst case hold, and everything has positive slack. And again, here these are the routes we were seeing earlier. If you double click on it, you'll now see that what they've done, what the tool has done, is move things around. We still had the required time, but now the actual time of the data path is longer than the clock path. And so now we have, if you look here at the slack, it's telling you that, okay, the arrival time is 1.988 nanoseconds. The required time is 1.967. So we have positive slack. And again, you could look through here, you could see the number of logic levels. You could see how you could then maybe decide you had to break things up or retime it, because sometimes you have to add pipelining to make things meet timing, things like that. So you can also look through here and realize that you have routes that need some pipelining or changes so that you can get them to pass timing. Into time summary. Okay, and now that I have a routed design, I can do the reporting power. So let's go ahead and do that. Again, this is the what we saw on the slide. So the process strength, it usually comes up with typical, and typical represents the statistical distribution of parts. And yes, the average part would be typical, but if you want worst case, you need to go to maximum, because there can be significantly more power consumed with the maximum process as opposed to the typical process. You can set your output loads. You can tell it where your ambient temperature is. Instead, you can tell it, you can do junction temperature and have it work backwards. You can do some estimates based upon heat sink and board, how many layers of copper are in the board, how much airflow. Again, these are first order estimates. They're not highly precise, but it gives you an idea of what you're working with. Power supply I mentioned earlier, you can put in nominal, or you can raise these up by 10%, 5% to get a more accurate result. You got your switching toggle rate of 12.5%, or you can choose a different rate. 12.5 has been known to be pretty good, but there are implementations that are highly pipelined that may need more. And then of course we can output to a file. Let's run it. Now again, this design is mostly empty. So there's not much going on in here, but it gives details. You can look at the hierarchical, which sections are drawing power. You can look at the summary, as we saw earlier, and see, I grabbed maximum process, the ambient temp, and then what the temporized would be. Right now, since it's mostly idle, there's not much in here. Most of the power is in your clocking circuit. That's what it says, 99%. And only a little bit, 0.007 watts is in your dynamic power, because it's a pretty empty part. Okay, so that's what I have in the demo so far. Let's go back now and take a look at some of our questions, because they may be demo related.
So just before we get to questions, I just wanted to pop in and remind folks that we do have one webinar like this one and a workshop, which is a day-long, no-cost event every month. So I'm going to put February's events into the chat panel for you. If you're interested, please sign up, or you can sign up for our newsletter, and then you'll get all of the events for the year. I've got the events posted through June. I'm about to post the ones for the rest of the year, so you can sign up for an entire series if you want. Also, if this webinar is interesting to you, we have some of our paid training coming up that is related to this. So I'm going to go ahead and put those classes into the chat panel for you as well, for you to check out. You might find them interesting. So if this webinar is something that you need to learn more about, our paid training might be something that fulfills that need for you. So Tom, I'm going to go ahead and let you get to questions, and I'll put everything into the chat panel.
Okay. Okay, so I see that someone asked for a report data sheet. I didn't get to that one, and that's not part of this demo. I can try it here in the moment. I don't know if it's set up properly or not, but I can run it. But let's get through the other questions first. Okay, so I see a question here. If we encounter hold time violations, what are the possible methods to fix them? Again, you're relying on the Vivado timing engine to actually do the heavy lifting. You could go in and manually move things around, like I showed, in the timing report, the implemented timing report, where it basically made the data delay longer than the clock delay. Of course, you could also maybe shorten the clock delay. Is a possibility, or maybe you could even have to go in and put an MMCM in and do a shift. MMCM, a mixed mode clock manager, which is a PLL, and you can do in your IO cells, because this was an input pin problem. Now you can actually advance the clock or delay the clock, and then to get the timing to work out. But in this case, there was plenty of routing capability. The tool knew to move things around enough to get a positive hold. Okay, how to produce these reports that can be made presentable into a document. As I showed with the tickle commands. If you want reports that are available to be used as into a text report, that way you can customize your arguments that you pass in, run things from the tickle command, and get just the information you want. And you may have to then bring it into Excel or something like that, or into a Word document if you wanted to do additional formatting. The other option is we have these GUI displays that are part of the window, and you could actually, and I've seen this done quite often, is do screen captures of the graphical results, and they can be dropped into design documents as well. How do you recommend constraining clock domain crossings, and do you use bus skew constraints for multi-bit CDC? Couple questions there. How do you recommend constraining clock domain crossings? Well, obviously you have to start off by defining your clocks in your constraint file, and giving them constraints as what's their speed, what's their, you can give jitter, you can give, or duty cycle, things like that, so that the clock engine, the timing engine can properly consume how much your clock dithers. And what speed it is, so what's the high time and the low time. And then obviously if you're bringing that in with data, you have to then properly constrain your input or output delays from outside. And that's, someone was asking about report data sheet, and that's where that comes in, because you're basically setting up your constraints properly. So at the pin, or based on what you expect it to pin, and again, the timing engine within the Vivado tool can then move things around to make it work. But if you're dealing with more advanced interfaces, you may actually have to do something with a clock manager to properly get the sampling to be right. And yeah, as you get the higher and higher speeds and higher performance, like DDR and things like that, well, then you get even more creative with these IO cells and configuring them appropriately. Now, you're also saying here, what about the multi-bit CDC? Well, if you're dealing with something where you've got, say it's just a bit that's or it's coming through, and there is a CDC bit cell that's in Vivado, you can have that. You can also create functions which are vectors created from that to get multi-bit CDCs. You have to make sure that you properly set up, and manage in your design, some kind of a handshake of when data is valid, so it can be transitioned. You probably should also set up an async reg constraint, so it tries to keep the bits together. Of course, if you use the IP that Vivado, that Xilinx provides in Vivado, The things like the constraints, like the async reg and things like that, they're already built right into the IP. So it's got its own XDC file as part of the IP, and it brings in all the appropriate constraints. Okay, I've got someone here giving me some recommendations of how I could have done a better demo. Understand that this is not a class, paid class. This is also, we have very limited time. I've only can show a very simple design, so I could actually pull out what is needed. But as Sharon mentioned, we have a broad range of classes, and we go into great detail of telling people how to do all of the things I'm answering now. Setting up the IO constraints, setting up the timing constraints, and how to drill into. There are entire classes that deal with just timing. So I agreed I could do a lot more, but with the 1 hour limitation of a webinar, this is all that I could fit in. Okay, so the question here, can I run a simulation to get a switching percent to feed into the power estimation tool? Absolutely. There is a, and I can't come up with the acronym offhand right now, but yes, you can run a simulator, whether it's the Vivado simulator, or say if you're dealing with simulators from other manufacturers. There is a standard file format where they can capture where all of the toggling is in there, and yes, you can then import that into your timing or your power report to give it better predictions. You can also bring that into your router, and it can actually do a routing based upon power optimization when you give it better information, like you're saying, with the switching tool. Okay, and the summary was put in here about what Vivado reports do we recommend for final design approval, and the timing summary, the clock interaction, and design rule check are absolute must designs that we have to as an absolute minimum to meet the requirements of a design checkoff. But as shown here, Vivado has a lot of different capabilities for generating reports that can help with it. And what is the difference between the design rule check and the methodology report? And as we talked earlier, the DRC report reports on thousands of discrete or defined rules, whereas the report methodology uses the ultra-fast design techniques to give you predictive results. So I think I covered the questions. If something was missed, please repost it. But we're at the top of the hour. If there are any other questions, please post them quickly because we're going to run out of time here.
Tom, thank you so much for telling us all about the design rule checks today. We really appreciate you sharing all of your expertise. And folks, if you want to drop any other questions into the chat panel, but we really appreciate you joining us today. We look forward for you joining us for future events here at BLT.
Okay, thank everyone for joining. I'm going to go ahead and shut down the webinar.